before anything, how many of your first years? Second years? Third years? Fourth. Sure. Okay, yes. So what you would have heard of the term topology for at least for I think second year onward. I think second year or third years would know probably. So what do you think of first when you hear the word topology?
Power set.
Power set. That is one. Then anything else? Collection of sets. Here. Okay. Then
Shapes and holes.
huh?
Shapes and holes.
That is good. That is good. And anything else? What else?
Compactness, algorithm.
Algorithm. Why algorithm? Why algorithm?
I read about it and I think
Okay, yeah, this is a good place actually. Algorithm is good. Then anything? Mostly the idea which I want you to, which I will be focusing on is that you have, every one of you know about continuity at least, for that matter. There is no, I hope that every first year, everyone who has joined knows about continuity. Continuity and in particular convergence, that is better, or the idea of limits. So we'll start from there. What the problem which I want to propose is that we have this definition of continuity. If someone tell me the definition of continuity for a function on real line, when is f continuous?
The epsilon delta definition.
Anything, whichever one you like, there's no problem.
So for a given epsilon greater than 0.
For every
Yeah, for all epsilon greater than 0, there exists a delta greater than 0 such that whenever
yeah.
Mod x minus c is less than delta, it follows that fx minus fc is less than epsilon. So if this condition is followed, then the function is continuous at c. So, and if this condition is followed for all r, then it is continuous at
Then
all.
it's continuous. Right. That's great. So the key phrase is continuity over here. Any other definition for continuity?
Same but with
For
for every.
every.
Like instead of for all epsilon, for every epsilon.
So those quantifiers are the same, right? For every, for all.
No, like this is uniform.
This is not
like
uniform.
the same delta for every epsilon.
no, that would have been
No,
there
no,
exists a
no.
delta for all epsilon.
Yeah. That is there. I would not.
Yeah, we will not
Whenever
see.
I would say whenever any 2 points, that would be if x minus x prime is less than something like this, if I'm not wrong.
Yeah, that's
Something like that. That is for every pair. Here the point is that we are fixing one point and then we are saying that with respect to that there is continuity. This is what you are referring probably.
She meant for all x after there exists delta.
or okay. This
Is that if for all x is in front, that would be a different meaning. Like that.
right. Yeah, fair. Yeah,
Just like delta of epsilon.
right.
We
Right.
need for all x.
Yeah, sure. Correct. Yeah, that's why this is the replacement for that. For every pair, if they are close enough and if it works in the same way, the same epsilon works. Yeah, so probably it would be better to add this with epsilon. Yeah, and not x. And here it would be epsilon and
X.
c.
X.
Right? Yeah. This would work. Yeah, this is good. So this is uniform continuity, that's good. That's one more. But let's stick to continuity. Any other definition for continuity?
F inverse of an open set is open.
Fair. We'll whatever words he's saying, we'll keep that as unknown. He's saying something. He's saying something. It's fair. But we don't know what he's saying. Any other definition of continuity? Which probably you'll have seen an analysis.
Sequence.
Sequential. What is a sequential continuity? That give next this is bad enough. By the way, you can if any notation doesn't make sense, if anything doesn't make sense, please ask. I'm not assuming anything.
Differential of real, what does that mean?
Oh, this is not differential of real, sorry. Yeah, I should define. So, when we say that some sequence is converging to a point, we are saying it with respect to some sort of a notion of distance. There is no conflict when it comes to probably real analysis. You can make conflict, but in general, the most useful version which we are studying, this is sort of assumed to be known. What is that distance in real numbers? It's a map.
Mod.
Which is basically as you said. Good. This is good. So with respect to this notion of distance, we know that this is true. Basically what we are trying to say is whenever these points are close enough or they are going towards x, then correspondingly the function will behave nicely. It will take the images of those points also to a fixed point. Right. This is good. So this is one more definition of continuity. So we got three definitions. Like one, this is for uniform, so we can keep that aside. One is the epsilon delta, which is all of them are equivalent obviously. Epsilon delta 1 and this using topology, what he said, which is we'll leave it as it is, and the one using distance or using sequences.
Are we saying that the distances becomes closer to zero? That's what we're saying.
Yeah. Oh, okay. So you want definition of this? What is this notation?
Yeah.
So this other notation which you would have known is probably n tends to infinity, xn is x, and this will mean that for every delta greater than 0 there exists n in n such that for every n prime greater than n this is what I mean by this notation. X and arrow x with respect to that distance. This is what I mean. This is convergence. So we'll call this as convergence. This one you can see. Okay, so I'll try to give Probably not. So let's keep these. Now, with topology, you would have heard continuity at least.
I have a question.
Yeah, fair.
So when you are taking a subset over there, you just wrote tau, but over here for the definition of continuity,
Yeah.
you took a subscript of reals. Why is that?
So these.
No, not in the metric. the
Second definition.
Second definition. F inverse of
The
B
open
belonging
set
to
one.
Second, yeah.
What did I take?
tau subscript reals.
Oh, okay, so this is not some fixed tau. There can be, you can choose any, you can choose power set itself, you can choose some other. This is just a way to index. It's a label. This is what is like a standard topology on real line, whatever that means. It's not. That's why I said this is fine, because this already assumes some sort of a meaning, which I'm not going to spoil for you. Right. So these are different notions of continuity. Now historically, yeah.
Is the sequential one only defined for this metric or like any metric this is?
I mean the continuity is metric dependent then.
Yeah.
So f is you could to be a bit more pedantic you could say f is dr continuous. Label the continuity with the metric, with the metrics, two metrics, whatever are there in the this side on this side. Right. There's one notion of closeness here. There's some other notion of closeness here. What he's saying is, does this have to be the same? Need not be. You can choose some other meaning rather than saying this. This one probably I can choose. Say this. Okay. So we check whether this works, but yeah. If I said this one on the other side, so that's basically a different notion of closeness, right? Than on this side. So I don't think this would work. I don't know, but yeah, we should check. Anyway, some other distance function could also work. Some other notion of closeness should also work. So the continuity should be tagged with the metrics. Is what he is trying to say probably. Okay, so this is good. We got very different, all equivalent definitions of continuity. Now, a little bit of history about this matter. So, up till 1906 is roughly the time where this starts popping up, and the context is that Hausdorff, there's a person called Hausdorff, his name is Felix Hausdorff. Yeah. So Felix Hausdorff is a person who works in analysis, right? He looks at convergences, but in a much more general setup. Probably you saw it in a real line. Similar sort of a metric or some sort of a notion can be given to more general spaces, right? So let's go to that then first. So we'll call D a metric if, what are all the conditions for metric?
Positive 0 for 2 of the same one. And triangle inequality.
Also, and and
Triangle inequality. You also know English maybe symmetricizing the
yeah, that is also there. So right. So these are properties which you would have seen in real line also. These are the conditions which are satisfied by mod, right? And this notion is generalized now. We take some set and we say that if these are the conditions, you know from your real analysis course, at least from real line and calculus maybe, that these are really the essential features which you use when it comes to proving things about limits, right? So yeah, so these are the crucial aspects which are picked up, and then they are generalized into a definition called metric.
So D here is a function from x cross x to R.
Yeah.
So x is a set.
X is a set, yes.
That is a Cartesian product.
Yeah, this is a Cartesian set. Yes, right. Good. Right. So these are called metric spaces. So this pair, or by abuse, this X would be called a metric space if it has such a function D on it. Right. And as you see, these are the notions which are somewhat required for defining convergence. Then we could talk about what it means for f to be continuous between, say, dx, y dy. Right? You could just repeat the same definition. The epsilon delta definition which you saw, you could just repeat the same thing over here. To be more specific, what would that look like for every right? So here you see like the only notion which is important is what is closeness meaning in that side and this side, and then we can repeat the same thing. So now you see this is much more broader. It already covers all our real lines, probably Rn. So rather than separately defining what it means for R1, R2, R3, all those, and maybe these sorts of spaces, this somewhat arrange them in an easier fashion.
So
And
f here is a function from x to y.
Yeah, f is
So-
a function from x to y.
So if we denote by the transcript y and z in different sets, basically. So we wrote x comma c with dx, and we wrote fx comma fc with dy.
Yeah.
That's the notation.
Yeah.
Okay.
Yeah. So, right. So, with the general notion of metric, we can subsume what continuity meant in real line, and we can take it further. And why was this necessary? Because if someone knows some odd metric on functions, can you tell me? On space of functions, can you define some sort of a metric?
Operators.
Yeah.
The operator.
Yeah, operator norm is. For linear maps, that is one
Yeah.
choice. What they are basically trying to say is, if I have, say, a linear map from I don't know, W, say this is isomorphic to Rn, this is isomorphic to. This is an example, so you don't need to be worried too much about the details. But the point is that continuity is a notion which holds in a much more general aspect than just your real line or anything like that. Wherever you see something which can be indexed by the real line, right? Say your functions, if you can write a family of functions indexed by the real numbers, f.1, f.2, so on, for all real numbers, and if you're able to write that, then you can try to induce what continuity means or what closeness means for the functions themselves, right? Basically some large sets, typically, you can take odd examples, but some things like that where a priori there is no notion, but because this semblance exists anyways of continuity, these ideas are extrapolated to such general settings, and that is why metrics are defined. One very good example would probably be something like integral of f minus g mod C1 problem. So if you have functions, let's take continuous because I think that is for whichever the integral makes sense. F and g are any continuous function. Functions going from what? X. Then with this probably you could say how close they are. Right. This gives a sort of a idea why we are trying to generalize metrics. And Hausdorff has this similar sort of a situation. But now the issue becomes more problematic. You see, in real line there is probably a very natural choice, geometric choice, whatever you have, which you have picked up. But when it comes to some general spaces like function spaces, there can probably be many options of metrics which all make sense. Yeah.
Could we also use the inner product functions? Inner product between functions?
Yeah, that's good. Yeah. So your vector spaces, yeah, right. They can have inner product, and inner product is like dot product. Dot product. So those are also notions of metric, right? And it would make sense to ask what continuity means for them. And because there's this notion of closeness, you can always try to ask if functions are nice enough to obey that or keep that structure intact. And now the issue was that with these function spaces for Hausdorff, that there were many sorts of metrics which he had to handle. So, but what they noticed was that the metrics were really not helping too much. They were a bit complicated because you had to keep track of every different metric, a different epsilon, delta all the time. So this was a bit of hassle. But what they were noting in their work was that there is something common for all of these metrics. There's some common notion for all of metrics, and the techniques were really not dependent on the metric in some sense. So the idea was so he gave the first formulation for topology, I think 1906 probably, where he defined this notion of closeness without metric, no metric at all. So for that a simple study is sufficient. So now we'll go to his definition of topology of whatever I was writing, that inverse V belongs to for every. Right. We'll try to make sense of it. The idea is that it is the same as the epsilon delta definition. First we'll define something called as a ball, open ball. This is an open ball. Basically what it's trying to say is, give me all the points which are in the radius r of the point 0. So they would obviously have y minus 0 mod would be less than r, and we are picking up all those points. So this is like a locality for that particular point, right? And with this language you can probably rewrite continuity in a better fashion. So what this would mean is, f is continuous. Again, I'm only talking about real line, so there's no if for every small v let's change this here. So this makes sense to you, that anything which is in the delta ball, delta close to the point x, will be mapped into the corresponding epsilon ball. That is what we had written, but in a different language where we explicitly told what that looks in terms of the metric. Now, this gives us a chance of this statement. This gives us a chance to go metricless. That is the idea. That then, if I were to ask you, in this sense, if you could tell me what is the entire F inverse of B what is this entire set?
B delta x.
What?
A set. No, not A set.
It obviously contains a delta ball.
Mm-hmm.
But the point is, anything you take here is like the nature of these balls or these localities is such that, or making the real line, take this. I had centered it around fx, right? But for anything else, I take the function. I am saying the function is like entirely continuous, so it's not at a point; it's continuous always. So I could take some point here. There would still be some smaller open or a smaller locality, for which I would again apply the definition of continuity, and I would get some other point here, right? Because say this is image of some fy, right? This is some epsilon prime ball which lies inside. Corresponding to that, I would get a delta prime around y, correct? Which should still be sitting inside epsilon ball. So then, what is this? This whole inverse is basically union of so say this is V. V is the inverse of the full epsilon ball.
Yeah.
It is basically composed of this all small localities or balls around different points, which are all part of its inverse. And this is a proper equality. There is no because we have essentially exhausted all points which were there in this neighborhood, right? We have picked everything. We have come back. We have checked the neighborhood. Still goes into the same place. So if we have collected everything, by definition, all the points in this inverse lie in this union. So now you see, whatever this was, its inverse looks like this. So like he said, let's call this open set. Okay, that's just a name. We'll call this some open set. And let's, for the sake of keeping it closed, like the discussion closed, we'll call this also open. So then this statement would transform to saying that inverse of open sets are open, right? The one thing which we require by just simply looking at is that the collection of these open sets is, or these neighborhoods is such that they are union closed. That is, if I say that there are some ui which are like localities like this, then the union of these ui's is also a locality. That is the, if we do that, then we call this collection of all balls, all possible balls on the real line. This is called as the collection, is called as a topology. The standard topology on R, with respect to which you have studied your continuity always, right? Yeah.
Two things. One, aren't we assuming the invertibility of the function on the?
Oh, okay. Yeah. Oh, that's a good question. So, I don't mean, so F inverse is not a map from R to R. F inverse is a map from because you see my inputs are not points anymore, they are sets, right? So what this function is doing is it's asking if I take a set y here, what all points of x are there which are getting mapped in y. F inverse is doing that. So by F inverse of a y, this is a subset, mind. I mean all points of R which get mapped into y. So this is a proper function. There is no, we don't need invertibility.
So I had a question in this. You're saying that V is equal to the union of delta balls
Yeah.
around all x in V.
Yeah.
But if we have an x very close to the boundary such that the delta is greater than that, and we overestimating V in that sense.
Yeah, but the point was that we are always, by definition of this continuity, we are always getting balls which will go into this. Even if that is, you are hit on a very good point. The idea is that what you are trying to suggest is very, very important, in fact, for our discussion. As we approach these boundaries, right, we are picking up points from here, 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 here. What if we reach a place which just, when gets mapped, it oversteps? But that won't happen. You know continuity, right? You know by the nature, that is what this strict inequality is doing. If I did allow, in fact, this, there would be a big problem. Then I would definitely overstep. But the point is, you know by the structure of reals, like, you know, between any two real numbers, there is always a real number, right? Just take average or something. There's always. You can keep going, keep going. So, you see this R on a real line, this is not part of the set, but it defines the set. Everything less than it is it in the set. So you can go as close, you can go as close as you want, but you'll never reach R. Yeah.
So
One more thing. You said that this basically removes the concept of a metric required for
I'll
quantifying.
go how?
But aren't we taking a metric in defining the epsilon ball? So if
Correct, perfect.
So
But I'll tell you, as I said, I didn't say it gives you, I said this has potential to go metricless. And I'll tell why this has potential to go metricless. And what he pointed out is a very important feature. Probably not now, but it will become very relevant in discussion, that open sets are something which exclude their boundary by nature. We have gone like that from the real line. We have chosen strict inequality rather than loose inequality. If we put this equal sign, that would mean that I am picking R as well, right? There could be a point which has the distance R from the center, that would be included. And then no matter what I would do, whatever would be mapped would cut this set, right? But the nature of this open sets is good enough that this doesn't happen. That is why we recover all this. Now, as I said, why does this have the potential to go metricless? See, the whole thing now rests upon defining what we deem to be close, right? A metric is a way to define what points we deem to be close. These are collections of sets, right? They're collections of neighborhoods. As much as an epsilon ball around X is a neighborhood, the whole of R is also a neighborhood, right? You can take union of, because I said they are union close, they would have to be, otherwise the definition wouldn't make sense. If they are union close, just take all X's, all unions of all balls, you recover the full line. As much as this is a locality around X, this is also. So there's a degree of locality. We don't want to be very exact, right? There's a degree which it is giving. Metric is doing it efficiently. It's giving you a direct way to, define these balls directly, and you're done. Okay, in fact, these balls, you see, they are dependent on metric. They are not really a feature of real line. As soon as I have a metric, you can define balls, and then you can define continuity in that fashion. That topology produced by the union of all balls is called metric topology on any metric space. It's just a name, anyway. So, right, what was I saying? That, yeah, so these metric give us a way to define localities. Now, instead of saying this, what if I said, I'll directly tell you a sub-collection. Instead of going via the metric, these balls, they are a sub-collection of the power set, which includes all sorts of sets, right? But the point is that the topology doesn't include all the sets. If you take the balls, they don't include sets like this, like the strict or the closed intervals. They're not included, even though they are subsets. So not all subsets are included. Some subsets are included to define this locality. What if I told you beforehand what they were? Instead of giving you a metric or instead of giving you anything, what if I directly told you what was the collection of open sets or these balls? That would work, right? Then I don't need the metric anymore. I can just scrap the metric. I have localities, I can just talk in terms of them. So this is roughly the idea which Hausdorff had. And now, I'll present the first formalism for topology, which is Hausdorff formalism. This probably you would not have seen in your courses. That let X be a set if we associate to each point X in X a family of sets N X non-empty family of sets N X which obey the following rules. Then we will call X to be a topological space. With the system of neighborhoods. So the first rule which we will take is, so now here he's trying to get to continuity point-wise. The point-wise definition is where you remember where we fixed one point and we're looking at all localities around that point. He's trying to pin down the features of that locality. That is, you have X on your real line, right? What are all sorts of localities which we saw in the real case? They just look like this, right? They're all just, I should draw larger probably. They all just look like this. They are just extending intervals so forever. And if you extrapolate these ideas, in fact, that is the idea of metric topology. That a neighborhood looks like this. That you just take balls of encoding radius forever, right? So he's trying to pin down what feature this family has of localities, because in some sense that gives you all the data about what points are supposed to be deemed closed, right? So now the rules which he chose, which I'll justify. First is that if U lies in Nx, then X belongs to U. Obviously the locality has to contain the point about which it is defined. If U and V, or if U lies in U and V lie in Nx, then U intersection V lies in Nx. Third, if U lies in Nx, then any superset containing U lies in Nx. And the last is if A lies in Nx, then there exists U subset of A such that U lies in Nx and U lies in Ny for every Y in U. Okay. So there are these 4 rules which he chose. I'll try to justify why he chose these. First is fairly clear that if a point is to be considered and a locality is to be considered, the point is included in the locality. We are not talking about some other localities of some faraway points, right? Then intersection. This is a bit tricky to understand why this holds. For a real line, you can see, for a real line by nature the intersection won't mean much. It's just subset. Every ball is a subset of some other, so the intersection would just be the smaller ball. It's included by nature. But this becomes important when you look at something which is which is more general. This is a bit more general axiom which he chose. This has relationship with how this is in some sense giving you a shrinking. He's saying that if two neighborhoods are supposed to qualify as neighborhoods of some point, then obviously their intersection is also supposed to qualify as a neighborhood, because it's a smaller set which is subsumed in both of them. So the points in that are supposed to be close to that point. That is the justification. But this justification is still vague. It's no proof. I'll try to make it concrete as the talk goes ahead.
If the intersection does not exist, there's no intersection.
Right. The first one avoids that.
X should be
The first one avoids it. So it's always X is there. There's no problem. This one, that if a certain set is a locality, then any superset is locality. This is a bit different from this picture. Here we didn't take, like, say, if I take some random point union with this open set, we didn't consider that to be an open set. But we'll consider it to be open in any case, because there is a smaller part of it which is local, or which is close enough. what this ensures for is the union portion is taken care of by this axiom. Like supersets are allowed, so all the unions are allowed. That takes care of this. The last one is quite important. This is related to symmetry. So you had so the notion of distance or closeness cannot be a one-way affair, right? So if X deems Y to be close, if it's too large, it's fine. But what this axiom is trying to say is if we go small enough, there should be some consistency to this symmetry. That it should not be Y just saying that these things are close to me, but those points never consider X to be close. What would be a violation of that axiom would be, you would keep getting points which are closer and closer to X. You can start somewhere, you can keep going closer and closer and closer to X. X calls them close, but then you will never see X in the neighborhood of X, you will never see in the neighborhood of Xn. So there is like a sequence which is converging to X, but none of those points are in fact consider themselves to be close to X. This is like a violation of symmetry in metric senses. What would that mean is like dx y is less than epsilon, but for some reason dy x is greater than epsilon. This is absurd for us, so we'll stay away from it. So these are the axioms which he puts, and he says this is topology. And why does this work? The definition of continuity works perfectly, and it subsumes all the features which you see in real life. What is the notion? So f is continuous at x if for every neighborhood, so these sets in the family are called neighborhoods. For every neighborhood ny, nfx, there exists a neighborhood nx such that f of nx lies inside n of fx. So as you see, this is a clear analogy of the definition which you are trying to get from the real life. We get this, and this works. But now you could ask why we chose these axioms at all. If we really wanted to make it general, would it not work if I didn't give any stipulation at all? Say I don't assume any of these axioms. There's no axiom at all. You can call the only axiom which I'll choose is probably that x lies in the neighborhood. Other than this, I'll not choose any axiom. Will the continuity still work? Any guess? Yes, no?
Yes, would be yes.
Yes, because the other three feel like they have been made to avoid any absurd behavior like my type.
Right. So
So
even if
first
we
one
leave
is-
them,
So even if we leave them, if we continue our processes, but with like be careful, we won't go wrong.
yeah, in fact we don't need to be careful at all. If I just remove this, there's no problem. We can still define continuity. There's no problem. But the point then this is a bit of a philosophical matter then. That this is a matter of choice. It's not a matter of force. Right? This don't force anything. The idea is that you don't add too many stipulations which are then going to negate something which you have already observed. Like if you say that I'll include all intersections, just not, this is finite intersection, right? If you include all intersections, there is a problem. What is the problem? If you take intersection of all balls around 0, what is the set which you get? 0. And is this open?
No.
In your like in the
No.
topology which you have looked at, this is not an open set. Right. So the only point which you need to take care of is you don't overstep or you don't put more axioms which are going to avoid or which are going to invalidate what you already observed in your places. But you can make it as loose as possible. There's no need to stipulate anything. Everything will still make sense. But the point is such continuity is almost useless. At least in the context in which Hausdorff was looking, that didn't have any relevance. He wanted to, his motivation was strictly from metrics. So these properties are somewhat, they're attempting to mimic what a metric does, but without the metric. Right? So then, what is the feature, what is the key feature of these sets? Why have these three been stipulated? If it is not something which is really required for it to be consistent. Any guess?
Well, 3 I think directly follows from 1.
3 follows from 1?
Yeah.
No.
No.
If u belongs to n of x, then x belongs to u.
Hmm.
Or right.
X is the point. X is the point about which we are describing.
implication,
It's
not
basically
equivalence.
all the neighborhoods are
Yeah,
having that
it's
common point.
An implication, not an equivalence.
Which implies what?
One, it's basically u belongs to n, x implies x belongs to u. I was thinking the other way as well. So that would then give us 3 as well. If x belongs to u implies u belongs to n of x, then
No, okay. You're thinking other way around.
yeah, it's thinking of the equations.
That would make it too loose. Like, if I were to say if x belongs to u and then it implies that u belongs to nx, that means any set which contains x,
Is a new
which will basically include all of this, whichever has x. And if we do that for all, because this is a general axiom, if we do that for all, then we are basically up to only one, this notion. Right. So,
Fourth property once again. I don't understand why that is taken.
right. So the idea is, like I said, it's about symmetry in locality. If you want two things to be close, can it be a one-way affair? Or you're allowing for it to be a one-way affair? That x can be close to y, but y can't be close to x. So, like I said, it would lead to sequences in perspective of x which are approaching, but in perspective of none of them, they are close to x. So if you want that, then you can remove that axiom, but if you don't want it, you have to keep it. So these seem like you could justify them somehow, but they don't, they're not stipulations. What is exactly the reason to define this? What do you imagine of when this goes to this idea, what he was saying, that in some sense open sets are supposed to avoid their boundaries, right? That is some feature which seems quite general, which doesn't seem to be in violation of any of this or anything of that sort. So I'll give another notion for topology, but it follows that takes this idea into account, that you could describe topology properly by just describing boundaries, sets and boundaries. So this is called Krotowski's formalism.
And so before that, could
Yeah.
you give an example of a space that is not topological?
Any set, like, I mean, which is okay. this would, so you want me to construct something?
Like just an example of a space that is not topological, so it doesn't follow these axioms maybe. So we have defined this a topological
So
space.
this is just a set. Pick any set. If I don't specify a topology, it's not topological. I didn't get the question.
So basically what I get from this is that okay, no, I was confusing it to be like, I was thinking, okay, R2, R3 can follow these properties, so they may be topological spaces. So I was thinking
They
maybe
are.
there, yeah. So I was thinking that maybe there's a space that doesn't follow these rules, so it could not be a topological space. But I get that it is set specific.
So this is too general. Like you
Yeah.
know, when this idea is, so that is also an interesting point which you have given, that at this point, like when he has defined this notion has left all semblance to reals. There's no you don't see real numbers anywhere here, right? So this has in some sense escaped reals. There's no mention of reals at all. There's no requirement of reals. If I were to speak, if I take the liberty and speak of in terms of like a more technical language, what that would mean is, this is not a concept of a specific category. Or what a category is, like there are some sorts of objects and they have some sorts of features. Like real line and continuous functions, this form a category. What is a category is that basically we are saying that there are some objects and there are some morphisms. Morphisms are these functions, sort. They obey some rule. First is that there is an identity morphism, right? So identity is there for your, it's a continuous function, it works, okay. Then if you compose two continuous functions, they are still continuous, that also works. Also the composition is associative, which is not even a feature which is required for continuity. It is true in general for sets. So in particular, sets as objects and functions as morphisms form something called as a category. Okay, so the category is supposed to tell you the behavior of the objects with just respect to the functions, with respect to just the functions. Okay, and in some sense this is an organizational tool which we use in math, right? So we will talk about groups or numbers or something like that. They form their own category, right? They have their own morphisms. For example, to be more precise, if you have heard of the term, okay, yeah, you know about linear algebra, right? So vector spaces are something, right? Rn, right? Rn are something, and then linear maps are something. They also obey these rules. Composition of linear maps are linear. Associated and all set theoretic features, so they are inherited. So those also form a category. So this basically puts all these objects in one place to be studied all together. Okay. Right. So
Also
that
my
is what I
original
mean by
question
category.
was that also because I was thinking that given any set I can form families around it. So
Yeah.
everything is a topology. Every set is a topology.
Every set has a topology, yes. You can give a
Every
trivial,
set is a topological space. Basically.
you can make it, yes. So topological space, for it to be, as I said, it would have to, the set has to come with something more, some more information, which always exists, but you have to still choose. There can be, because a single set can have many topologies. For example,
A different family of sets.
right,
Okay.
like in the case of metric spaces, as I said, the set is the same. If I choose different metrics, then what? The set is still the same, but the topology is different.
Okay.
Right? So topological space is this data, that there is a set and there is a notion of closeness
Okay.
with it, which comes. But you see, this was even up to metric spaces, this was bound by the notion of reals, right? And what this does is that lifts this idea of closeness from reals at all, and it puts it to a much broader category, which don't require anything to do with reals. So I don't know if I should say this or so this set category, right? So this is something which is called as forgetful and equivalent, or basically these you for any set you can produce some topology, right? What I could do is I could just choose, as you said, I could remove, I could choose power set or what neighborhood you describe, right? For every point, I'll consider all sets which contain X to be a neighborhood. This will take in all the subsets, right? This is a topology. This doesn't violate any of the rules.
Yeah.
So any set always has a topology by nature,
Yeah.
and it can have more than one topology,
Yeah.
right?
So I think
So-
that's the fact. The fact
Yeah,
that
yeah.
the set can have more
So
topologies
the
is
point,
interesting.
yeah. So the point which you're getting to is this definition has lifted the concept of topology from a particular category to something which is more free. There's no requirement of anything at all, seemingly. So, right. Yeah, now we come to a more structural feature. It's captured by this thing called Grotowski's formalism. What Grotowski's formalism says is that we describe something called as a closure of a set. Okay, what is the closure of a set? On a real line, this is your open set, this is also your open set, the union, because I said it's union closed. So all of these are open, right? What is the closure of this set? What he said, we have to include the boundary. If we include the boundary, then it's closed,
Yeah.
right? It's closed. So what will be the closure of this set?
So-
I'll denote it by this notation, bar.
The same set but containing its limit points.
Perfect. So closure of this is just it's strict inequalities.
Yes.
Correct. It has included its boundaries now. So and you see, what if I chose the idea that that is all that is needed to define topology. That if a set excludes its boundary, then it's open. But we need to give a way in which you can assign something as boundary, right? Here what is guiding you to say that something is a boundary is a metric. Remember, only because you have that mod function, you are able to tell that this is a boundary point or this is a boundary point. If I don't give you a notion of this metric, you won't be able to tell. But I could do it like I did it in the case of neighborhoods. I just defined them ad hoc. I could give you that information ad hoc, that I'll tell what are the boundary points for every set. Then would that be a sufficient information for defining topology? The answer turns out to be yes. There are some rules, so which we said. Okay. So this is called, we define something called as an interior operator. Like closure, there is an opposite of that. It's the interior. So say I gave you some set, this. What is the interior of this? We want to exclude the boundary.
Exclude the limit points.
So this would become like this and this. We have just excluded the boundary, we are fine. And whatever is doing this information was given by metric or something, but I could give you directly. You tell me the sets, I'll tell you what its boundary is, then that should suffice. Right? So that information I'll call it as this association or interior. This is an operator. This takes sets in, gives out sets. But what it does is it just excludes the boundary. Now what properties make this operator sensible? First thing which you would notice is interior of some set A should lie in A. We are not including any more points, we are excluding. So obviously this is good. One more.
Interior of interior is just interior.
Idempotency, yes. This is very good. that we have already excluded the boundary, there is no more boundary remaining to be excluded. Okay. One more property. There are two more, but yeah.
Every interior is an open set.
We'll come to that. We don't need that for now. Third is interior of or I have made some mistake. It should be union or intersection. I don't remember.
Union does not.
Should be union.
It should be. It should be.
Union.
I think it should be intersection.
Union does not work.
Huh?
And if you take two closed sets, like say 0, 1 and 1, 2, their interiors will give you the two open sets. It would not have one.
Yeah.
So the union does not give you the interior of those two sets. The union of
Yeah.
the interior of those two sets doesn't give
But
you.
what about intersection?
I think intersection.
Should work. Yeah. I think it works. But yeah, this is a bit of non-trivial part. This is the same sort of a thing. What is happening here? We are demanding intersections to be finite intersections to be closed. Like if you take intersection of two intervals, it should be an interval. Like that. We are stipulating something like that, but it's a bit fishy. It's not very clear. This won't become clear now, but it is going in some direction. We can take it. Last one is a bit trivial. Like it's not something which is that illuminating. Interior of your full set is your full set. That your space does not itself have boundary.
Okay.
It's already boundaryless.
So it's already open. Basically.
Yeah, it's already open. Your full space. There's like it's like asking you're standing in a world and what is outside the world. You don't know. Or what is the edge of the world? You won't be able to answer such a question. Because that is all there is to know.
But what if, say we are
To
working
give this notion of a boundary for a space, you would need an embedding. Like it is residing somewhere else, then you could tell that there is some boundary, right?
Yeah.
Because even to imagine if there is nothing outside, what would you say? Right? So these are the notions, and what we do is, if any operator, these are just properties, this is not a specific operator, right? These are just some properties which you have stipulated. If any operator phi obeys these properties, it's called an interior operator, and image of phi, or what is the other? Image of phi or interior are the open sets. Right. There is a bit of a work which you have to do, but yeah, there's one more which I'll give, which is a short formalism which all of you know already. This is a modern formalism, open set formalism. That instead you'll define just the full topology of the space. It has the following rules: that find x belong to tau if a family is subset of tau implies union alpha T alpha belongs to tau, and if u and v belong to tau implies u intersection v belongs to tau. This also works. In this case, what we are basically doing, how to go from here to there, these two are the same things, surprisingly. The idea is that this last notion, this fourth notion, it is telling you about a shared neighborhood, right? The points which truly consider each other to be close. Take all of them to be open, they satisfy these rules. You can check that. These two are equivalent. and you can show these two are equivalent.
Equivalency between this and that.
Yeah.
How is our n of x?
How is that?
When equivalent, when we are equal, whatever is the term,
making
is
it
this
equivalent.
and that.
Yeah. How do we get n of x, right?
No, n of x is tau over there. Am I getting that correct?
Okay, yeah. So I'll tell you. Sorry. I'll tell you the path. So you define tau with respect to the system as n x such that nx is a shared neighborhood. This information you know from there. The fourth axiom tells you that any neighborhood has a smaller portion which is shared by all its points, right? So those are shared neighborhoods. If you take the collection of all shared neighborhoods for all points, you get topology in your modern sense. Those sets obey these rules. Intersection falls out from there, union falls out from the superset part. Phi, okay, yeah, you have to do a bit of, you have to add phi.
Because of the
Yeah.
So the third axiom you have taken that any superset of a
Yeah.
neighborhood is also a neighborhood. It's not really equivalent to that condition, right? Of unions.
Closed sets can be.
So you can have a closed set containing an open set. By that axiom, that closed set will also be a neighborhood.
It will be a neighborhood.
But here it won't.
But it won't be a shared neighborhood. So this, what I have written over here, it's supposed to be a shared neighborhood. What is a shared neighborhood? That is stipulated by this fourth point. You could go on, adding points, some arbitrary points, doesn't matter, God knows what not. But what that axiom says is, for each such neighborhood, there is a shrinking possible. This is what the content of the fourth axiom is. There is a shrinking possible which reduces it to something which is genuinely a neighborhood for all its points. And those actually correspond to what you think of when you say open sets.
Okay, so in the closed case you won't get so the boundary points you won't be able
Yeah.
to shrink to them.
Yeah. So for the closed set, what you'll run through this axioms. In the last axiom, you will get a set which is shared, and that will exclude the boundaries. So you get all of this. You can check that there. Okay, from here, how do you go there? Any idea? If you have this information, if you have a topology, how do you define a neighborhood system? It's quite trivial, but just take supersets of all open sets, right? They are the shared neighborhoods, but if you include all supersets, by definition, they satisfy the other properties. So that is the way to show that those two are equivalent. The more non-trivial work is to show that these two, it's simple, it's some algebra, but to show that Grotowski's formalism is the same as open set formalism.
When you say that they're equivalent, you basically mean that
Given the data of that sort, you can produce a data of this sort, unique.
so meaning ki if I have a function here in this setting, and the function is I deem it continuous with this, it should be continuous there also.
Everything is correspondent. Because you see, the burden of continuity has been lifted to defining what neighborhoods are. Right? We post the point where we addressed what the neighborhoods are, we didn't even care about continuity at all. The burden of defining continuity was shifted to defining neighborhoods. Right? So, yeah. This is a bit of a work which you have to do, but this nonetheless gives you the same. These two are equivalent. So all three of them are equivalent. So these are the three formalisms for topology. And now we'll go for something which eliminates all our problems in some sense. All the ambiguity which we had with respect to intersection and whatnot, we'll try to eliminate it for once and for all. So this this is a bit of a non-trivial idea which it takes. So yeah, as this development was happening, this was all good, like just use neighborhoods and you are able to describe everything. But it was still a problematic situation because more or less people were still in analysis. People are still dealing with epsilon delta. It's just that there are too many epsilon deltas. It's too bad to deal with. So the main problem still exists. There are multiple metrics, even though you have given this neighborhood formalism, because you are working with actual epsilons and neighborhoods, right? You are not able to get rid of that, and sequences are still important. So there is some sort of an issue that you can't simply leave all of that and go to these kinds of formalisms. So now a bit of development happens. There are two people called Moore and Smith. Moore and Smith do a different job. What they do is, you had given me the sequential definition of continuity, right? Or sequential definition of convergence. Let's forget about continuity for once, because that definition of continuity relies on definition of convergence or limits. So we can shift to talking about this, right? What happens to these when we go to topological spaces? Right? We have already seen that defining closure, boundary or interior, all of them give you topology, right? This should give you boundary, right? In some sense. A point is in boundary of E. Let's take E. E is a subset of X which has some topology tau, modern formalism. E is a subset of X. Now X lies in closure of E if and only if there exists an index to n subset of E such that Xn converges to X with a lead to tau. Is this true for the present topology students? You have your point set topology, right? You should be able to answer. Is this true? That X lies in the closure of E if and only if there is a sequence inside E which approaches X. Is this true? Yes, no?
No.
No? Okay, you have to justify why no.
Because if, let's say, this definition follows for a limit point, right? So what we're saying is, if X is in the closure of A, the closure of E can contain other points other than limit points, so that wouldn't follow.
You're talking about if X, then you can just take Xn to be X now. So if you're
So it's a constant.
Yeah, constant sequence.
Okay.
Works.
Only one direction is obvious.
Which direction is obvious?
If there exists Xn and E such that Xn.
Right.
Then you know that X will.
That's true, yes. Okay, good. But other way?
other way also it's
Can be defined.
Yeah, you know, so the point is, you have these neighborhoods. Now we forget about shape, everything is lost. We are in a general space. They can have any sorts of shapes. Right? X is some point. All the sorts of neighborhoods have been taken now. What that would suggest, the other way around, for it to be true is that you are able to produce a sequence which has the convergence property. That eventually it lies in all open sets around E. That is a bit of a work to do. How would you choose that? How do you choose such a sequence? You don't know about the neighborhood system, right? It can be like absurdly large. This is true in some sorts of spaces. What are those spaces? You know the definition probably. Some sorts of topological spaces, this is true. Okay, the spoil. Okay, the answer is they are two in first countable spaces. I'll tell what they are. For general people, this is a property of the real line. Okay, your neighborhoods, you don't need to consider all real radius. Taking rational radiuses suffice, because there is always a rational radius ball sitting inside any real radius ball. This is by, what is that called, Archimedes? Yeah, whatever. So, or like it just follows from definition of reals, really. But yeah. Anyways, so you have this luxury exists only in some spaces where your neighborhoods are countable. Your neighborhood should be countable. Then the choice is given, right? You have a countable set of neighborhoods which you need to account for. For each count, you choose 1 point. So say you have this data. F is the family of open sets around X, right? Then you can choose, but this is countable. So what you will do is you will arrange it in a certain fashion. Take some u first. Then whatever else you take, you just take intersection. If it's not subsumed or something like that, you keep doing this. This will still produce a countable choice. And now you pick one from here, one from here, one from here, one from here. Like that generates a sequence. But to do this in general spaces is not possible. A space, okay, where is this violated? That's a more non-trivial task, but where is this violated? But it is important wherever this is violated. Well, so first countability is not necessary condition, is sufficient. The necessary condition is actually the statement itself. Like that is like if where did that go? E closure. Yeah, if this is true, those categorize the spaces themselves. If this property holds in those spaces, they need not be first countable, but those are more non-trivial matters. But an example for this, where this doesn't hold.
Where first countability does not work.
First countability doesn't hold, and for that matter, this thing doesn't work. This real analysis 2 or something.
Could you again explain why they need to be countable?
They don't need to be countable.
I mean,
the point. Oh, okay. For
yeah,
real.
countable.
For real.
Yeah.
Okay, that is good. So you have x, right? X is for delta. Delta is greater than 0.
The
Can
delta
you
neighborhood
choose-
basically, right?
Huh?
Delta
Yeah,
neighborhood.
delta neighborhood.
Yeah.
Can you choose a rational number which is less than delta?
Yes.
What is it?
So between delta and
Zero.
less than delta. Yeah. So density of rational. So you can choose.
Right.
Yes.
And you're done then. So you don't need to work for every real. Every real neighborhood you choose, like every real radius neighborhood, you don't need to account for it because there's a smaller neighborhood which is of rational radius. So if you account for the smaller neighborhoods, you're done, right?
No, I don't. My question was, you said that this is only valid for countability.
Countable
Yeah.
neighborhoods.
So why
Yeah.
was that?
Oh, why that? Yeah, because I justified this, right? Not only countable, I said it can be true in general, but it's easily realized when the space is first countable. That is because of this. That you choose the neighborhood, you keep taking intersections, so you shrink the neighborhoods. This shrinking is done in a countable fashion. And you pick one point from here, x u1 intersection u2, x u1 intersection u2 intersection, okay, u3, so on. This defines a sequence, right? This sequence converges to x.
But why can we not have uncountable intersections and then?
Okay.
You're saying that
So-
we have countably many intersections and then
Right.
it corresponds to
Correct,
that.
correct.
But
so
why
now
can't-
now you have given the answer for what I'm about to do. The problem is a sequence is by nature indexed by naturals. What is a sequence?
Yeah, it's a function from n to r.
This is the problem.
Okay, then it has to be countable.
Whatever you call, it's not a sequence. It's something else. It's not a sequence anymore. If you're indexing by
Yeah.
some arbitrary
Then it has to
neighborhoods.
be countable basically because it's
Yeah.
with n.
Yeah. Only then you will call it a sequence. These are sequences, right?
Mm.
So he gave the answer basically. So why stick to this index set? There's no problem. We make it larger, right? Rather than, because if there are uncountably many, we just need to give a rule so that the index is proper and it covers all these possible neighborhoods. Because if you are able to index anyways, this same argument will work, right?
Oh.
To produce this sort of a thing, these need not be countable. Fair. Fair. So this brings us to the one of the final formulations. It's called nets. So we move from sequences to something called as nets. What is a net? So first we define something called as a directed set.
What is the counter example for the previous one?
Oh, I didn't tell you that, right? Yeah, sorry. So you have to take this space. This is the, okay, what is this? This is a Cartesian product indexed by the reals of reals. Okay, and you take, so this is the space of functions basically, real functions, right? Because what is this? For each index of R, you're getting an R. So the space of all those functions is this, real functions. These functions, you have to set some sort of a topology on this to make this possible. The topology which I'll spoil is pointwise convergence. Whatever is given, whatever topology you choose for pointwise convergence, which is product topology. In fact, this is a very good place to do this. Product topologies and such were defined for these matters. Because the idea of pointwise convergence corresponds to the space having product topology. This is some jargon for third years or so. Okay. So yeah, this is the space. You can work it out. Yeah.
Can we take like real numbers like co-finite topology or something?
Cofinite is a very good example. Cofinite is a very good example because it's not first countable, but the thing is it still works in cofinite, unfortunately. Unfortunately, that is the case, and that is the extra part. Why that is not necessary condition for this to hold. The closure to be related to sequences need not hold because of that example. In cofinite topology, that lemma still holds. Okay. Right. But anyways, what we managed to take out from here is that sequences are good. Right? They help you describe the space. There is some problem which we have to fix. But the idea is that once we give you this, you can describe boundaries. You can describe a closure operator and go all the way back. What does this mean then? If I tell you, so this is the final idea, okay. The final idea is that you give me a set X. Okay, for now suppose that sequences don't cause all the problems which you are seeing. For now let's assume that. Then if I tell you sequences are still defined, there's no problem of defining sequences without topology, right? So there's some sequence in this space. Actually, this takes to the final idea that what if limit is just labeling? If I just label this sequence with some point,
Okay.
right? If this is just a notation for associating this with this, there's no need for any topology here. And when will this give me that? One is when it's in where it is good enough in first countable, but the point is as soon as we strip off this, we'll have to give some property for this data so that we recover topology. That I'll come to. That is what Moore and Smith did, and that they did it for nets obviously. So now we'll define net. Before net, we need to define something which is called directed set. Does anyone know what a directed set is? Any graph theory students? No? Okay. So a directed set is a set with a pre-order. I'll define whatever. So there's some order on this, okay. Some less than equal to sign is there, which works. The properties which this has is that if lambda belongs to this lambda, then lambda is less than equal to lambda. First property. Second property, if lambda 1 and lambda 2 belong to lambda, there exists lambda 3 such that lambda 1 is less than lambda 3 and lambda 2 is less than lambda 3. Okay. This is basically saying that take any two element, there is a larger element. The first one says that the thing is greater than or equal to itself.
So they are ordered.
Yeah. This is reflexivity. This is something else. Then the third one is transitivity. That if lambda 1 is less than lambda 2, lambda 2 is less than lambda 3, then lambda 1 is less than lambda 3. Okay. This is a directed set. We'll take these as indices. And now is the crucial construction. Why is this sufficient? Do you see this property somewhere already?
Like insets, but with sets with that. I mean, for the second property, I need more.
You don't need more actually. You already have it.
Yeah.
Oh yeah, sure. Huh. Okay.
This is
What do you have?
Like if I was thinking if I take the set to be the max set, then I wouldn't have something but x is less than equal to.
No, but it's not going up actually. It's coming down.
Okay.
Intersections are always smaller than the other two things.
Acha.
So you just
Okay.
reverse. Right. And why? So now you see why it is good enough. Because the data of open sets around a point, it always has this, its intersection closed. Right. So you always have this smaller element. If one thing is smaller and the other thing is smaller, then obviously they are smaller.
Right.
Then so transitivity holds and reflexivity obviously holds. So it's sufficient. So this works as an index set. So what becomes because of this is that, okay, now we define net. Net is the map P going from lambda to x is called net coordinate next if lambda is a directed set. Right. Okay. And with this definition, you have that lemma, what I was trying to give you. No first countability required, nothing required. For any topological space, it's true. Obviously, by nature of construction. And that is called as a directed set corresponding to the neighborhood. So, how would we define? U is less than V if V is contained in U, and rest of the things follow. Just reverse it. So basically shrinking. Going down is, you could make, the direction really doesn't matter. The properties are what matters. And it's taken care of. Right. So because we are able to index all of these neighborhoods, a job is done. For any topological space, what we get is X belongs to E closure if and only if there exists a net. Mind you, this lambda need not be fixed, because obviously the neighborhood systems are changing. For each to account for, we'll have to keep it flexible. And obviously it subsumes sequences. The sequence is a net. If there exists a net, P going from lambda to X, which we denote by X lambda and Y lambda. X lambda converges to X. Convergence, we give the same definition. What will be the definition for convergence?
You can open set. There should be something.
It's the same sequence style that for every neighborhood U of X, there exists lambda belongs to lambda such that for every lambda prime greater than or equal to lambda, X lambda prime belongs to U. Eventually the net lies in the open set. It's the same as sequence. We just change this index set to make it larger. Right. So this works. And now we come to the final theorem. That let's describe topology. Oh, by the way, continuity and all are defined in analogous fashions, and all of them follow. They have the same definitions. Like if X lambda converges to X, Fx lambda has to converge to Fx. So these things. Let's describe topology. Right, now we press on the idea which I gave you, that what if instead of giving you a topology, I give you all nets which converge and I tell you where they converge. Will that be sufficient to define a topology for which that is happening? It turns out it is. So a net data provided, but it has to obey some rules. Can't be any net data, obviously. So what properties does it have to obey? We are basically trying to recover some things. First is X lambda equals to X for every lambda, and X lambda approaches X, goes to X. Second is if There is one for each closure axioms. So basically these will become the same as closure axioms. For each closure axioms we have to stipulate a net axiom.
Let me check.
Okay. These are all things which you have seen in analysis. X lambda converges to X implies every subnet converges to X. What is a subnet? Okay, yeah, that is a bit non-trivial. So a subnet of P is a composition P composed phi, where phi is a map from m lambda to lambda. These are two directed sets, and phi is a map going from one directed set to the other. It just needs to obey some rules. The rules which it needs to obey is that it is co-final, like you don't stop somewhere, basically you keep going, so there is a large enough phi lambda. Lambda and anything else. Yeah, I think this is okay. So it also respects the order, that is lambda 1 is less than equal to lambda 2 implies phi of lambda 1 is less than phi. These two, then that composition describes something called as a subnet. It's like a subsequence, right? Because the subsequence is you're choosing some indices, and in this fashion you're not going backwards, you're going forwards, and you're choosing large enough for everything, you're not stopping somewhere, right? Yeah, so this is second property. Third property is that this is a bit icky, but I'll justify this. If for every subnet of a subnet of X lambda, it converges to then the original net also converges to X. This is required for the idempotency, that when you're considering idempotency, take closure axioms because you're creating a closure. So what we have over there is that closure of closure is equal to closure, right? So that would, what are the, in the sequential level, what would that mean is you pick some subnet here, corresponding to that there is some subnet here which converges.
Could you also justify why every subnet needs to converge to X in the second axiom?
This one?
Yeah. Why does every subnet needs to converge to X?
See, it's like you're reducing the data, right? You have a sequence already. It is
Index by lambda, right?
Huh?
Index by lambda, right? The sequence?
Yeah, index by lambda. You have a sequence. It's like you're cutting off some points in the sequence.
Okay.
Would it change the convergence?
No.
But the reason why we choose it to be a defining feature is it corresponds to this axiom that your closure is smaller than closure is larger than your set.
Okay. Yeah.
To prove that you need this. You need this. This you need to show for basically x is the closure, like x is its own closure. Or sorry, phi is its own closure, sorry. Phi is its own closure. For that you need this. For this, this is for that one. The last one is the worst one, which is required for the intersection or union in case of closures. The closure of unions is union of closure. For that you need this. This is the main theorem by Moore and Smith. It's called Moore and Smith's diagonal lemma. This is also true, like you have seen this in sequences already. That consider if there is a sequence x lambda, and for every lambda there exists a sequence x mu lambda which converges to x lambda, and say this converges to x. Then there is a subnet of this itself can be taken as a net. How lexicographically? That you choose one of the orders, you pick lambda to be the bigger order, then with respect to each, first you check with that, then you check with the second order, mu, which corresponds to each particular lambda. So you get your lexicographical system. That on n cross n, what would that mean? One comma 2 is smaller than 1 comma 1. First we check with the first coordinate, it's the same, so it doesn't matter. But in the second one, okay, this is wrong. Yeah. Right, this is the lexicographical order. We do the same thing. So there is a subnet of this as a subnet converging to So with these four axioms, we don't need to use open sets or anything of that sort. If I give you a data which obeys this, it will produce you a topology. You will create a closure operator which obeys Krotow's case formalism, which is same as following modern formalism. Right. This does close the matter, but now, so this was already, I think, 1940s or so, 1940s that this work happened. This was done by Moore and Smith. But now, Henri Cartan, he works in analysis, and he's like, indices are also too much to handle. You don't want indices for some reason. So this you can read about it. It's called epsilon management. So people in analysis, they would probably know. So it's called epsilon management, that you have to keep track of a natural number, an index and a radius and blah blah blah. By removing the metric, you took care of the epsilon, but you still have to manage this index now. So it's like even indices are too much, get rid of them. So we do that. So this is by Cartan. Cartan defines something called as a filter. Filter. What is filter? You already know an example of filter. Neighborhood system is an example of a filter. I'll define what it is. So a collection of subsets. Like say F is a filter if intersection closed. And superset closed. If U and right. Now what Cartan tells is that instead of saying that there are some points or sequences which are going to a point, you simply say that this family of sets itself is going to that point. And how do you do that? So for this we'll use neighborhood data because that's just easier. Neighborhood or model, anyone works. So we say limit of f is x, or another notation, f goes to x with respect to some topology obviously. If the neighborhood filter, neighborhood is a filter by definition, neighborhood system is a filter, is contained in X. So basically your filter is finer than the neighborhoods. So that would mean that for every neighborhood you have it included in this, right? So it's like those points are by set taken into those neighborhoods. So it's like sets approaching to a point rather than points approaching to a point. So what that would mean is, by definition of neighborhood filters, this is true for tau, because obviously they contain subsets, right? And again, with respect to this, the same lemma holds. Everything holds. That the closure is an element of closure has a filter which approaches to that point. What would that mean? Okay, let's just write that down. So X belongs to E closure if and only if there exists F such that F belongs to F as F subset of E and F a filter. Okay, so yeah, this is the idea that instead of considering your index directed sets or whatever, you replace them all together and you just keep track of sets, neighborhoods themselves, and you see other things as neighborhoods, as filters.
But would we not be indexing the collection ultimately as well of the subset? Would we not be indexing the collection of subsets?
There is no that's done by that's done by construction. You don't need to account for it. In a proof where you're writing, there's no index for this filter, right? What is the definition of convergence of a filter? It does not involve any index. Have I mentioned any index here? It's just that it includes the neighborhood filter. Right? Yeah, so that does the job. And all the things which I said follow already. Function is continuous if it takes convergent filters to convergent filters, blah blah blah, so on and so forth. Right. And so with this, Cartan removes even indices from the question. So this is the final epsilon management. Don't need indices, you don't need epsilon, just work with filters. And for this, so you will be surprised. which, okay, now that I've spoiled it already, but which is a larger in some sense? Is a filter formalism the same? Are filters same as nets? There's a hint in the definition of filters, but yeah. Are filters nets? This will make you realize how large nets are actually. They are actually. So the filters are nets. How are they nets? So you have this property. Use this to create the index, as we did in neighborhood, right? Because that's all we needed. So if, okay, just let me erase this. Right. So given a filter f, how will we produce a net? So what we do is we do something like producing a graph of a function, right? Say u is a member of f, then we take x and u. U is the index, x lies in u. Or if for better notation, you can just write it as xu. This is a net. You can check it. You have already checked it, but yeah. And obviously we don't lose out on anything. Okay. But you need to go from this way to that way also. A net is a filter also. How do you see that? That is actually very important. That hits the nail on the intersection property, which we wanted from so long to justify, right? So this idea is already there in sequences, so you know it. It's like if you have two epsilons, you pick the smaller one. That is the idea of intersection. You take the shorter tail of the sequence. You skip the longer one, right, by taking the larger n. That is exactly what we do in intersections. Why the intersection axiom is stipulated everywhere is because of that reason. Because sequences work like that. That if you have two sequences converging, or is the same sequence converging, and you get two informations, one from one neighborhood and another from the other. The neighborhoods which we are used to work like this, that there is a smaller neighborhood for which it still works, the convergence still works, right? And that's why we need intersection. The proof for in the case of, I think it's evident in the proof of why intersection of open sets are open. You choose the smallest epsilon for finite, like there are finite choices to make. For two, if you do, it's done. So yeah, more or less that. Yeah, how do you produce this anyways? The filter corresponding to a net. Say you have a net x lambda. I gave you the hint already, but yeah, let me do it. It's faster that way. What we do is we define f lambda to be x lambda prime greater than equal to lambda. The tail of the filter, the tail of the net. So basically we are chopping off the first part, which is less than this lambda. So if the sequence was like, it's basically saying that if it was x10, so f10 would be everything including and after 10, right? And why is this a filter? To see this as a filter, you have to check those properties that it's obviously superset closed. Can you check that?
Superset. Wait. I mean, if I have to. Wait.
Like the theorems and convergence.
Yeah, but that you have to include it in indices, right? We could take like awfully many points. I'll leave that for your exercise. Intersection is a bit easier. Yeah, by transitivity you pick the smaller or some, yeah, you take the supremum of the lambda. That gives you the intersection property. But yeah, superset is a work. It's some work you have to do. But this more or less justifies all the axioms which we assume in every formalism. Just in consideration of modern open set formalism, unions make sense in terms of these sequences, because it doesn't matter how larger the head you make, it's the tail that matters, right? Keep making it larger, it doesn't matter. The intersection property is similarly justified. So with this, we are sort of done. Yeah, and then there is a analogous result for filters also, that filters describe topology. And how you would do that is, in that case we went through like closure axioms and whatnot. In this case you just have to define what would become your neighborhood filters. If you do that, then everything else works out. Right. Yeah, so this brings us to, so now you see, we have successfully lifted the idea of sequences, like made it more broad or general through filters or nets, and correspondingly we have lifted convergence, and so as a consequence we get continuity also, and topology as a given. So this is generally left out in curriculum. No one will tell you why we are choosing those axioms, but these are the reasons. And now about the other things. Now I'll just speak freely, because now like the matters are more technical. There's no way I can just avoid the jargon, but I'll try to clarify as much as possible. So filters are not only useful in like topology. Topology obviously. One more thing. These all other things like compactness. You have the net-based definition or filter-based definition, and the idea is, how do you define compactness in terms of sequences? Every sequence has a convergent subsequence. So even in this you have something like that. Every filter has a convergent subfilter. Every net has a convergent subnet.
Every bounded sequence has a convergence.
Okay. Like that. So with that you get compactness, and Tychonoff comes off as a very easy corollary. So what does Tychonoff's theorem say? Tychonoff's theorem says that if you have Cartesian product of compact spaces, then the Cartesian product under product topology is also compact. Okay, how is product topology defined? Product topology is defined by projections. That if you force projections to be continuous, you get product topology, right? And you have this lemma that your projection functions are obviously continuous. So you take some filter over here, f, use pi alpha, push that filter down, project that filter, the set is compact, converges to a point x alpha, lift it back up, you have a choice of x alpha for each alpha, Tychonoff done, because then your f converges to so you do some other business side like some finite intersection property and whatnot. Is it too early? I don't know. Like for the course, I guess it's not. For the people who are taking now, third years, I don't know who are third year. Yeah, you're taking now, point set. So Tychonoff is still late. So that is written. That just comes off as a easy corollary like this. Then there are then actually filters are used in logic also. First order logic, if or model theory, if any of you have studied. Have you studied? Yeah. So there is okay. You at least you would have heard of non-standard analysis, right? So there is something called as something which we define as star R. Star R is the hyperreals. Hyperreals. How are the hyperreals constructed? So you take the direct, so Cartesian or direct, what do you say? Direct union, not direct union.
Disjoint union.
Disjoint union, yeah. Disjoint union of all like reals, copies of reals over some index, and then you quotient it by some property. So the property is that these are these are very large numbers, basically very large or very small numbers, and this equivalence property is basically a filter. You quotient these products by filters. In model theory, what you would say is you have this would become structures mi quotiented by a common truth. So what this means is if a formula works for if in mi psi holds for almost all I, for this you need filter for almost all I. What we mean by almost all I is given by the filter, because you see we are basically categorizing tails, right? So by almost all we mean you can leave out some things always. You can keep leaving out things, finite things, but that won't matter. And if this truth holds almost always with respect to a particular filter, then the truth holds for, then the formula holds for any structure, collection of structures. So this is called as a, this is called Wash's theorem or something. There's a Polish guy. So he proved this. This helps in construction of hyperreals, and all the, so this basically, because of this what happens is everything which is almost always true for reals is true for hyperreals. That is why you get this like infinitesimals and whatnot still work. Like you recover all results of your analysis, but there is something more which you get. But yeah, this is one application of filters. Then in categories. So categories, as I mentioned, what they are. there is a concept of limit and categories also. So, if say F is a category, then if the morphisms, if you have a directed system, what is a directed system? Algebraic geometry, you should know.
So you're talking about direct limit.
Yeah. Direct limit, inverse limit both come off as a consequence of this. So you have objects xi and psi I and then object x such that and you have fij. Basically you have xi and fij such that if there is this map fij xj, if there is phi j, right, phi I is commutes. So this is a directed system, and this is related to the directed set which I was telling you, because here your index is a directed set. You need to take you take a functor from any directed set, it forms a small category, and you take a functor from that to this other category, which basically is labeling. Labeling is the functor. So you label all this and you get correspondingly this, and as a consequence of this, these you can define limit of this functor label lambda, and this is your final object, initial object, whatnot, or it can be inverse limit, direct limit, and a more general version of this and in fact your filter is also you can make your filter to be a category, then the limit of your filter is the direct limit. And more or less the like these categories and this sort are left out, right? They don't teach.
Yeah.
Yeah, but these are the applications which I wanted to talk about. Okay, that's it. This is the topic. Anyone wants to ask anything?
When you're going from this filter to net link, so like you're invoking the axiom of choice now to like choose the...
Yeah, we do. Even for existence of those choices which we make for so there is this idea of something called as an ultranet or an ultra filter. They are like maximal filters. For them you need choices. For these I don't think you need choice.
How do you build net then from filter?
How would I take, because firstly these are fair, you need